the same.
All right, there we go. Any questions before I sort of pick up where I remember our leaving off? Yes?
The course entry assignment?
Yes.
It said today was the last day to do it.
Yes.
I didn't see it on Blackboard.
So if you go to start here, it should have been at the bottom.
Yeah, it wasn't there anymore.
Oh.
I checked it maybe, I don't know, 2 or 3 o'clock today. It wasn't at the bottom of the page.
All right, at the break, I'll go see what I missed.
Okay, and I'll double check it again here in a second. Just
Everyone else found it?
I haven't done it yet. I found it. I did that last book.
All right. Thanks for letting me know. Any other questions at the moment? Colin, I assume the head shake means it's not there?
No, that was another question. I'm still pulling it up.
Oh,
It's just the
okay.
stuff.
Sorry, misinterpreted the head move.
You said it should be at the bottom of coursework?
Start here.
Start.
Somewhere near the bottom, if not the very bottom.
No, I don't see it on here anyway.
Okay.
No.
Right. Other questions? All right. We last left off where we were trying to find the force on a charge outside something that had spherically symmetric charge. And so we got through it and we ended up showing that if we are outside something with spherically symmetric charge, we can treat this like a point charge at the center, which is a really convenient shortcut to take later on. Now, let's move the point inside. The only thing that's changing are the limits of integration. We could start from the beginning and go through the whole bit, but I'm just going to jump straight to this part of the formula here. The order might be slightly different than what I had written before, but in essence, this should still be the same. Alpha is just some constant up front. We'll worry about alpha later if we need to. So now we are dealing with this spot right here. What is the force? So this is some charge Q1 that's bundled into alpha here. What are the limits of integration now? So it's little r, the distance from the charge basically from some point on the sphere to the point in question. What's the smallest value little r can be? 0. Not if it's inside. 0 would indicate that it is sitting right there on the surface. It's inside my sphere.
R minus L?
Big R minus L.
Yeah, big R minus L.
So if the distance from the center to the surface is big R, and this is L, then the shortest distance is this right here. That's the shortest distance of L minus big R. Oh, sorry, R minus big L. Unlike what we did before, where it was big L minus big R, this is big R minus big L. What is the R-just value of little r? What's the farthest away that we can be?
Big R plus L.
So that's the calculus problem we're dealing with. And so like before, we break it up into parts. I'm going to take my r squared over r squared. So I've got this alpha integral of r squared dr over r squared from r minus L to r plus L. And that's a capital R there, in case you can't tell. plus the integral of big L squared minus big R squared over little r squared dr from r minus L to r plus L times alpha. I couldn't remember what symbol I used for the constant up front before, but so it's alpha now. Well, the first one, the r squareds cancel out conveniently. And so we're just left with an integral dr. So what is the integral of dr?
R.
All right, so r going from r minus L to r plus L. Now let's go ahead and finish this one off. So that's alpha times r plus L minus r minus L, which is 2L alpha. Over here, we have the integral, my alpha up front, integral of L squared minus R squared, R to the negative 2 dr. I don't know which form you prefer, whether you prefer the writing it like a fraction or the negative exponent. I'm a negative exponent man myself, but whichever one you need in order to figure out what is the integral of this. Big L squared minus big R squared. L is a constant because it's in a specific location, and big R is the size of my sphere, and that is also fixed for the problem. So I got a plus alpha L squared minus R squared, that part I got. What's the integral of 1 over R squared, or the integral of R to the negative 2?
And at negative r to the negative 1.
From R minus L to R plus L. So here we got alpha times L squared minus big R squared. I got a negative out front, bring that negative, and then I have 1 over R plus L minus 1 over R minus L. Looking at just the second part here. Okay, negative alpha, and then I'm going to distribute my L squared minus R squared here. Recall difference of perfect squares. L minus R times L plus R. So I multiply times the first term, and my R plus L's cancel out. So I'm left with L minus R minus. Multiply times the second one. It almost cancels out. I'm going to be left with a negative 1 because my denominator is R minus L, and this is L minus R. So I'm going to have an extra negative sign thrown in there, so that's negative L plus R. So I get negative alpha, L minus R, plus L minus plus R, which is minus alpha times 2L. And so if we bring in the first part of the integral plus the second part of the integral, what is the total force?
Zero.
So what we're dealing with here is that if I am inside the spherically symmetric shell, there's no force acting on me. I should probably reword that. A shell with a spherically symmetrically charged charge distribution, uniform charge distribution. There we go. It's like a Faraday cage. Now, in reality, if I have a charge here, it's going to change the distribution of charge, but it's a decent enough approximation. If the charge on the shell is large enough and this is small enough, decent enough approximation to assume that inside the spherical symmetric charge distribution, that the force acting on any charge inside would be 0. We'll justify it a little bit later once we get to electric field.
So anything that happens in that shell is basically ground zero and nothing happens to it. But so
if I've got a single charge in there, yeah,
Yeah.
nothing happens to it.
but so the electrical forces, are they on the outside of that shell?
There are forces. If again, I got some charge shell. Any charge on the outside has a force acting on it.
Okay.
Anything on the inside has no force acting on it. If I bring that charge inside, no force is acting on it. In our nice ideal world. I don't know if I actually addressed what you were asking, but did I? Sort of.
Yeah, enough for me to make sense of it.
Okay. Now, how realistic is have a uniform distribution of charge? Well, if I've got a conducting, let's say a solid piece of metal, spherical solid piece of metal, and I charge it. I take some excess charge, I put it on the ball, on the metal ball, and the charge hates each other. The electrons, if I'm putting electrons on it, the electrons will scatter, and they'll scatter until they are covered uniformly around it. They're not going to be on the inside because they move easily. So if I've got an electron on the inside and the charges have not distributed themselves evenly, then it's going to keep pushing on those charges on the inside until everything's on the outside. Basically pushes everything away. So if it's a solid ball, excess charge will be on the outside. If I strip electrons away, then the remaining electrons will move around until we have an even distribution of positive charges on the outside. If it's an insulator, I just have to rub it with a rabbit fur evenly around. At least close enough. The charge will stay on the surface, and inside will be neutral in a sense. We'll revisit this again once we talk about electric fields. Questions here, because I'm going to take you down another fun-filled calculus-based romp with uniform charge along a straight line. Yes, it's about to happen. Now, one of the reasons we're going through these is the math in 252 verse 251 is more sophisticated. We have to do more sophisticated math in this course than we did in the other one. So part of this is just sort of get you into that mindset of the beautiful relationship between math and physics. And if you already appreciate the beautiful relationship there, well, you still have to suffer through it. Surely it can be better than that. Try this one. Not a whole lot. Uniform charge distribution. Lambda. I'm using U. I forget what your book uses. So, lambda is what I'm using in my notes. So when I say uniform distribution, I can take any length of this, and I look at the charge. So the charge within this length, so the charge per unit length is constant. No matter what size length I pick, if I take something half that size that has half the charge. Of course, we can make this calculus-based because it doesn't matter what size I pick, that my charge distribution is just dq dl. I use the lowercase l for the small segment. And so if I take some charge here, some little charge q, I want to know what is the force acting on q. Oh, by the way, when the charge inside, we got that the charge inside the spherically symmetric distribution, the force on it was 0. That's one that sometimes in class, that's the one I do instead of starting with the one on the outside. So we went through, just imagine going through all that math and ending up with 0 at the end. I find that's incredible that you go through all that sophistication to come out with such a simple answer. Students, on the other hand, sometimes think that, why didn't you just tell us it was 0 to begin with? So I thought you would appreciate having the one that did not come out 0 first. I did it for you. All right. What we're going to do is we're going to establish a coordinate system here. And I'm going to establish my coordinate system, boom, right there. Make that the origin. And as before, I start out with some little segment of charge here, dq. And I'm going to figure out what the differential of the force is between dq and little q, and then integrate over the entire line. That's supposed to be straight. That distance there would be little r. The distance from Q to where the line is, just to keep some synchronization with my notes, I'm going to make this big R, because you can't have too many R's in the same problem. And this distance from my origin to where my differential of charge is, I'm going to go clever and just call that x. And so the length of line that I picked right here, I did dl for sort of the generic, but specifically for this one, this would be dx for this, the way I've defined things. Probably would have made more sense if I stuck with that distance being L, but I didn't. All right. Now we don't know what Q is, whether that line is positively charged or negatively charged, but we assume it's positively charged and then work through the whole thing. If it turns out it's a negative charge, it doesn't change our formula. We just, the minus sign shows up when we put in charge and it flips the direction. In other words, what it's claiming here is that there's a force in that direction. This is the differential of the force from dq. We are dealing with vectors, of course, and so we need an angle. And so which two did I pick? No, just the one. This angle right here is theta. So that angle right there is theta. So I have two components to my force here. I've got a force that is part of the force that's acting down and part of the force that's acting to the left. And then we're going to do something the math people can't do. We're going to reason through the answer and move on. That's part of the answer. So the F has a x component acting downwards, and it has a, try that one again. It has, in typical math speak, it has a y component and a x component, or a horizontal component and a vertical component. Recognize for every dq I have here that's a distance x to the right of my origin, there's a one over here that is to the left of the origin. When I add up the total force along the line here, for every force, horizontal component of the force, I've got another one that's in the opposite direction. You can justify it, you can go through the math to actually come out with the answer, but we can reason through it, and that any horizontal component of the force is going to cancel out with something else, so the total horizontal force is 0. The net force acting on the charge Q, little q, is down. I only have to worry about the vertical component. So my force that I care about, K little q dq over r squared, the basic Coulomb's law, plug it in. But now we want to deal with just the vertical component, and so sine of theta. And now let's make down j hat. J hat. For the math purists in the group, there is another component. I'll make I hat to the left. Plus I hat kq dq for r squared cosine theta. And when you integrate, the second term is just going to go to 0. That's the part that we reason is going to go away. The physics argument, ultimately, integrate 0 by symmetry. It is legitimate to do in physics. Just make sure you're right. And once again, we're going to do an integral where we have 3 variables. And we need to get it down to 1. So I'll start doing step by step. First off, let's deal with dq. I know dq is equal to some constant times my differential of length, and I keep kicking this. Hopefully that will reduce the number of times I kick it.